Welcome to True Projects. In this video, we are going to explain about the project entitled as Explainable AI-driven dew point forecasting with attenuation-based temporal convolutional networks. So before getting into the video, let me give you the brief description about the project. The title describes a method of predicting dew points using advanced deep learning models that analyze time-dependent weather data. Attenuation-based temporal convolutional networks help capture important historical patterns affecting dew point changes. The use of explainable AI ensures that the model's predictions are transparent and understandable, improving trust and practical usability. Coming to the abstract, this abstract explains the importance of accurately forecasting the dew points for various real-world applications such as agriculture, eviction safety, and climate analysis. It highlights the limitations of traditional forecasting models, particularly their inability to handle complex time-dependent patterns and their lack of transparency. To address these issues, the work proposes an explainable AI-based framework using attenuation-based temporal convolutional networks, which effectively captures long-term dependencies in meteorological data. The inclusion of an attention mechanism allows the model to identify the most influential features and time periods affecting dew point predictions, while explainability techniques improve interpretability and user trust. Overall, the proposed approach achieves higher accuracy and robustness than existing methods and provides valuable insights into the factors driving forecasting decisions. Coming to the existing dew point forecasting system mainly uses traditional statistical techniques such as linear regression, arrhythmia, and numerical weather prediction models. Although these methods work reasonably well for short-term forecasting, the struggles to handle complex nonlinear patterns and long-term dependencies in meteorological data. Advanced deep learning models like RNNs and LSTMs improve prediction accuracy but requires high computational resource and suffer from issues such as vanishing gradients. Additionally, most of these models functions as black boxes, offering light insights into how predictions are made, which reduces transparency, trust, and their adoption in real-world weather forecasting applications. Coming to the proposed system or base paper work. The proposed system uses an attenuation-based temporal convolutional network to accurately and transparently forecast dew points. Temporal convolutional network efficiently process time series weather data by capturing both short-term and long-term dependencies through casual and dilated convolutions, while require less computational efforts than recurrent models. The integrated attenuation mechanism identifies and emphasizes the most important past term steps and features that influence dew point changes. Additionally, explainable AI techniques provides clear insights into how the model makes prediction, improving transparency, trust, and decision-making support for weather dependency applications. Coming to the data set, the weather data set from Kaggle consists of historical weather observations collected over a continuous period, with each record representing atmospheric conditions at a specific date and time. It includes a mix of numerical and categorical attributes that describes various weather parameters such as temperature, humidity, wind, pressure, visibility, and precipitation, along with textual summaries of weather conditions. The presence of time-stamped data makes it suitable for time series analysis, while the detailed meteorological features support in-depth weather pattern analysis. Overall, this dataset is well suited for dew point prediction, weather forecasting, and the development of machine learning and explainable AI models. Coming to the novelty or extension or enhancement or improvement. As an extension to the base model, two advanced architectures were developed, BiLSTM plus BiGRU and hybrid attenuation plus BiLSTM plus BiGRU. These models combine the strength of bidirectional learning and gated and recurrent units to better capture complex temporal dependencies in weather data. Among all the evaluated models, The BiLSTM and BiGRU model delivered the best performance, achieving a very low RMSE of 0.016 and a high R-square score of 99.38%, indicating highly accurate dew point predictions. To enhance transparency, the ELI5 explainable AI techniques was applied to interpret feature weights, helping users understand how different weather parameters influence the model prediction. And a user interface implementation. A Flask-based web interface was developed, allowing users to input weather parameters and obtain dew point predictions directly using the trained model. And next, the system was further extended to forecast dew point temperatures for the next 1 hour and next 6 hours, with results displaying on the front end for improved usability and practical decision making. Coming to the flow of the work, firstly, we have importing the packages. This module handles importing all required libraries and loading the weather dataset. Initially, exploration is performed to understand the dataset structure, identifying the missing values, analyze data types, and observe basic statistic characteristics of weather attributes. Next, data pre-processing and feature engineering. In this module, the dataset is cleaned and transformed to make it suitable for modeling. Future engineering technique was applied to generate meaningful inputs, and explainable AI-based feature selection using SHAP is performed to identify the most influential features for dew point prediction. Next, we have the data visualization. This module focuses on visual analysis of the data set. Feature importance plots and correlation metrics are generated to understand relationships among variables and validate the selected features. Next, data splitting and normalization. The process dataset is divided into training and testing sets using 64 by 36 split. Feature values are normalized using minimax scaler to ensure consistent scale and improve model training efficiency. Next, model construction and training. This module involves building and training multiple deep learning models, including LSTM, CNN, CNN plus LSTM, by LSTM, GRU, TCN, and attenuation-based hybrid models. Each model is trained with optimized hyperparameters to learn temporal patterns in weather data. Next, extended model development. As an extension, advanced hybrid models such as BiLSTM plus BiGRU and attenuation plus BiLSTM plus BiGRU are developed using 80 by 20 training test split with minimax normalization to future improve prediction accuracy. Next, model evaluation and comparison. This module evaluates all trained models using performance metrics such as ME, MAE, RMSE, MAPE, and MASE. Models are compared numerically and visualized to identify the best performing architecture. And next, explainable AI integration. Explainable AI models such as Line and SHAP are applied in this module to interpret feature importance and explain the model's prediction, improving transparency and trust. Next, we have forecasting module. This module performs short-term dew points forecasting. It includes sequence creation, time-ordered training test split, normalization, and trained for the selected BiLSTM and BiGRU model to forecast dew point for further time horizons. And next we have front-end and deployment module. This module implements a user-friendly web interface using the Flask framework with integration and login functionalities supported by an SQLite database. Users input weather parameters which are pre-processed and passed to the trained model. The predicted dew points values are then displayed on the front end for user interaction and decision support. The algorithm used in the project are LSTM, CNN, CNN plus LSTM, BiLSTM, GRU, TCN, attenuation plus LSTM, attenuation plus CNN, attenuation plus CNN plus LSTM, attenuation plus BiLSTM, attenuation plus GRU, attenuation plus TCN, and as an extension, we have done the train and test split according to 80 is to 20% ratio. And then we have normalized by using minimax scaler and we have added the extended models like by LSTM plus by GRU and attenuation plus by LSTM plus by GRU. Coming to the requirements, we have hardware requirements and software requirements. Hardware requirements consisting of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework is Anaconda, primary language is Python, front-end framework is Flask, back-end is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap 4. To execute this project, first we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python, which handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contain the algorithm information which will be loaded into the project code during the runtime. Notebook.ipynb file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Now, coming to the execution of the project, firstly, you need to copy the path of the code folder from the address bar of the file explorer. Then, open Anaconda prompt. By using the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the link provided by the framework and paste it in any web browser. I prefer Chrome. The home page of the project should now be displayed in the browser. This is a front-end built using the Flask framework. In this page, we have Home button and Register button. Now, click on Register button so that the logon HTML will be opened. Here, we need to give the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Then click on Create an account so that all the given details are stored in signup.db and the login.html will be opened, where we need to access the application by username and password. Now click on Sign In so that the prediction page has been displayed. In this page, we have prediction button, data visualization button, notebook button, and logout button. Firstly, click on prediction button so that the prediction and forecasting will be opened. Now click on prediction button so that the prediction form will be opened where you need to enter the features for the prediction. So first we have trend. The value of trend is minus 4.19844. Day or night, in the night the value is 1. Day or night, the day value is 0. The time cost value is 1. Time sign value is 0. Season summer value will be 0.866025. Month cost value will be, season summer value is 0. Month cost value will be 0.866025. Season rainy value will be 0. Month sign value will be 0.5. Season winter value will be 1. Day of year value will be 1. The year value will be 2012. Now click on predict so that the input values are pre-processed and the output will be displayed as minus 4.13 degrees Celsius. It is the forecast dew point temperature. And we also have the result analysis, and dew point details are like forecasted values, humidity level, comfort index, typical range, and the weather condition. And we also have the visualization like the dew point temperature scale, which means it has been stopped in between the cold and moderate. And here we have make other prediction. When you click on this, again the prediction form will be opened where you need to give the input values and predict the output predictions. So as of now, we have done with the prediction, and now click on forecast so that the forecast configuration form will be opened where you need to upload the CSV file. Firstly, click on choose file. You need to upload the file from the test cases in the forecast like sample1.csv. Then click on select forecast horizon like for next 1 hour or for 6 hours. Now click on run forecast so that the input is pre-processed and the output will be displayed as forecasting visualization. We actually treated for forecasting for 1 hour. This is a graph. And next we have recent forecast for last 25 rows. And here we have the download full forecast CSV button so that we can download. And here we have back to prediction button so that the prediction will go back for the forecasting form where you can enter the other sample CSV file and predict the forecasting. Now click on data visualization so that the graphical representation of the project will be opened. Here we have show all graphs button where the all graphs will be displayed, and we have data analysis button. If you click on this, only the data analysis graphs will be opened, and model performance, if you click, only the model performance graphs will be opened. And here we have explainable AI methods. When you click on this, the explainable graph will be opened. So firstly, let us check one by one graph. First, we have global feature importance using SHAP graph. This graph shows the global importance of input features in dew point predictions based on mean absolute SHAP values. The 10 features has the highest impact, indicating the long-term temporal patterns plays a dominant role in the model's prediction. Features such as relative humidity, temperature, and station level pressures are contributed noticeably, while other time-based or seasonally features have relative smaller influence. Overall, the graph highlights which variables mostly strong drive the model's decision, improving transparency and interpretability. Next, we have correlation matrix graph. This correlation matrix visualizes the linear relationship among the engineered temporal and seasonal features used in the model. Strong positive and negative correlations can be observed between related features such as day-night indicators, sine and cosine time encoding, and seasonal variables, confirming correct features encoding. For example, month and season features show how correlations, while cyclical encodings exhibits complementary relationships. Overall, the graph helps identifying feature dependencies and multi-collinearity, supporting informed feature selections and improved model stability. Next, we have actual versus predicted values graph. This graph compares the true target values with the values predicted by the hybrid bi-LSTM and bi-GRU model across a sequence of samples. The close overlap between the actual and predicted curves indicates that the model is generally able to capture the underlying patterns and temporal dynamics of the data. While there are small deviations at certain points, reflecting prediction errors or noise, the overall alignment suggested good predictive performance and consistency of the model across the dataset. Next, we have R square score graph. This bar chart presents a comparison of R square scores for different machine learning and deep learning models, illustrating their predictive performance. Models with higher R square values indicates a better fit to the target data. The graph shows that hybrid and attenuation-based architectures generally outperform single or basic models, highlighting the benefits of combining multiple learning mechanisms. In particular, bi-LSTM by GRU and attenuation bi-LSTM by GRU achieves the highest R-square scores, demonstrating superior accuracy and stronger generalization compared to convolutional models such as LSTM, CNN, and GRU. Next, we have MAE graph. This bar chart illustrates the mean absolute error for different machine learning and deep learning models where lower values indicates better prediction accuracy. The results shows that advanced hybrid architectures generally achieve lower MAE compared to basic models, reflecting more precision predictions. In particular, bi-LSTM by GRU and attenuation bi-LSTM by GRU exhibit some of the lowest MAE values, highlighting their effectiveness in minimizing prediction errors. Conversely, certain attenuation-based combinations shows higher MAE, suggesting that model complexity alone doesn't allows guarantee improved performance. Next, we have RMSE graph. The graph illustrates the root mean squared error values for various deep learning and hybrid models, where lower RMSE indicates better predictive performance. Overall, baseline models such as GRU, LSTM, and GRU achieves relatively low RMSE, showing strong accuracy. Several attenuation enhanced models improve performance further, while others practically attenuation plus TCN and attenuation plus CNN exhibits noticeably higher RMSE, indicating weaker performance. This comparison highlights that attenuation mechanisms can enhance accuracy while well integrated, but the effectiveness depends strongly on the underlying model architecture. Next, we have test loss graph. The graph represents the test loss values for different machine learning models, where lower loss indicates better generalization on unseen data. Standard modules such as TCN, GRU, bi-LSTM, and bi-GRU achieves very low test loss, reflecting strong and stable performance. Some attenuation based model, including attenuation plus LSTM and attenuation plus TCN, show noticeably higher test loss, suggesting potential overfitting or less effective integration of attenuation. In contrast, hybrid attenuation models like attenuation LSTM plus CNN and attenuation by LSTM plus by GRU maintain low loss values, demonstrating that attenuation mechanism can enhance performance where appropriately combined with robust architectures. Next, we have validation loss graph. The graph illustrates the validation loss for different machine learning models with lower values indicating the better performance and generalization during validation. Baseline models such as TCN, GRU, LSTM plus GRU exhibits consistently low validation loss, suggesting stable learning behavior. Some attenuation-based architectures, particularly attenuation plus LSTM and attenuation plus TCN, shows significantly higher validation loss, which may indicate overfitting or reduce effectiveness on validation data. In contrast, hybrid attenuation models like attention LSTM plus CNN and attention by LSTM by GRU maintain low validation loss, demonstrating that well-designed attenuation integration can improve model robustness and validation performance. Next, we have adjusted R-squares graph. The graph compares the adjusted R-square values for various machine learning and deep learning models, showing how well each model explains the variability in the data while accounting for model complexity. Overall, most baseline models already demonstrate strong performance with high adjusted R-square values, but hybrid and attenuation-based models generally perform even better. In particular, combinations like attenuation LSTM plus CNN, by LSTM by GRU, and attenuation by LSTM by GRU achieves the highest scores, indicating superior predictive capability. In contrast, some attenuation-based variance shows comparatively lower performance, highlighting that attenuation mechanisms are most effective when paired with suitable model architectures. And finally, we have explainable AI sharp graph. The graph represents a sharp summary plot that illustrates how different inputs influence the model's output. Features are ranked by their overall importance on the y-axis, while the x-axis shows sharp values indicating whether a feature increases or decreases the prediction. Color represents the feature values with blue indicating low values and red indicating high values. The plot shows that trend T1 has the strongest impact on the model, followed by day-night indicators and seasonal variables which can either be positive or negatively affect predictions depending on their values. Time-related features such as sine, cosine, transformations, and yearly components have relatively smaller impacts, indicating they contribute less to prediction variability compared to trend and categorical temporal features. Next, click on Logout. So finally, the study shows that attenuation-based temporal convolutional networks can accurately forecast dew points by capturing key temporal patterns with meteorological data. Explainable AI techniques highlighted the most influential factors, making the model transparent and interpretable. This approach outperforms traditional methods, offering a reliable and actionable solution for weather-dependent applications. So this is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.